We have three speakers today, Steen Moeller, Caroline, and David Feinberg. We're going to do proper introduction a bit. We were also meant to be joined by one more moderator, Rita Smith, who unfortunately could not join in today due to the ongoing situation in the Middle East. So unfortunately, it will just be me and Aaron. And that each talk is supposed to be 20 minutes long. We have 10 minutes of discussion after that. You can raise your hand if you want to raise a question to any of our speakers, or you can use the Q&A function or chat, and we're going to try to do our best to read out your question. And without further ado, I will give the floor to Aaron to introduce our first speaker.
It's my pleasure to introduce Professor David Feinberg. He's a professor of neuroscience at the University of California, Berkeley, in the Helen Wills Neuroscience Institute. Dr. Feinberg is a pioneer in MRI. His research is focused on the development of advanced MRI technologies, including high-resolution fMRI, and he's contributed to the Human Connectome project, including multiplexed EPI, and currently working on the next generation 70 scanners. And I'm looking forward to hearing his talk now on tuning your hardware for fMRI. Welcome, David.
Thank you. Yes, I was asked to talk tuning your hardware for fMRI. I can talk about hardware development and certain generalizations that one needs to consider with hardware in our development of a scanner. So we decided to pursue the funding for the NIH Brain Initiative, which was offering a particular call for developing next generation human brain imaging technology. And it was to be transformative work. And I, at the time, was involved with mesoscopic fMRI work. So what could be better than to design and build a new scanner for high spatial resolution circuitry studies with layers and columns with fMRI as well as diffusion imaging. We knew we wanted to go down to sub-millimeter resolution, and to achieve that, we proposed a scanner design with several new subsystems, the gradients receiver system, the shim array, to achieve this higher res. And the overall rationale was that combining the improvements in each subsystem, you get cumulative gains in SNR or acquisition speed. So we wanted to have several areas of improvement. And the final scanner design, compared to the proposed, ended up with Siemens coil gradient group built a gradient coil with very impressive performance, 900 slew rate and 200 millitesla per meter. We have only proposed going to 150 maximum. We have not yet completed the local shim array, but we're working on it. So it's the first 128-channel receiver system that's allowed us to optimize receiver arrays, and I can talk about that. And the whole goal was to get high-resolution brain imaging. So the scanner, as you can see, was assembled in Berkeley. This has the Siemens Terra scanner magnet, and it began right when the COVID pandemic was declared the week later. So we were, to some extent, on our own, working through Zoom calls with Germany scientists, but we got it together with field service engineers' help, and the coil builder that we ended up really pulling us through was Shahjahan Gunamoni, one of the coils, the 96-channel coil. And it took a lot of testing because these arrays had never really been developed or tested, nor had the gradient coil. So we went through several copies with improvements of gradient coils and receiver arrays. The gradient coil had a 44 centimeter inner diameter, which was about 10% larger than the previous head gradient coil, and allowed a lot of space for different types of hardware. And here you can see the gradient coil in this cartoon schematic in the magnet. It's only covering the head and shoulder regions, so it avoids cardiac stimulation, and it also is a smaller diameter, allowing for a difference in inductance and switching the coil. So you could go to very high slew rate, which you cannot do with a gradient coil covering the body. And also unique about the coil is the inner layer of winding that has never been done before. And that was by Peter Dietz, the gradient coil designer. So the results were published in paper at the end December of 2023, actually November, and describes the hardware and some of the preliminary results. So what's so special about our gradient coil? Well, as I mentioned, it has a third additional layer of winding that had never been used in a gradient coil before. The conventional shielded gradient coils have an outer layer of windings that cancels the field to eliminate eddy currents in the magnet cryostat. But our intermediate third layer allowed us additional degrees of freedom to adjust for eddy currents and torque forces, and as well as peripheral nerve stimulation. There was modeling done during the development of the coil by Matthias Davids, then a graduate student, and that ended up going into the design, wiring design, along with other model approaches, and his modeling of the red here showed a very high threshold for the X gradient, which you use quite extensively for echoplanar imaging, transverse images. And at the factory, testing was done, and you can see the blue with the gradient coil outside of a magnet, not in the scanner. And it seemed to be, the simulations, experimental results seemed to coincide, which was really impressive and exciting. But when we got the gradient coil to Berkeley in the scanner and started imaging, we found that the stimulation was more frequent, and we reassessed the peripheral nerve stimulation. And I won't spend a lot of time on it, but it was much lower than the assumed values. And this could be attributed to several factors, just a wide variance among subjects, and even the age of the subjects. And we're now using sort of the average of the two populations combined to get what's called the safe curve, first guess or setting for a maximum rise time on the slew rate shown here on the operating curve of 900 millitesla per meter. So younger subjects have a lower threshold. We looked at by combining and having over 60 subjects in the combined study, and older subjects. The mean in Germany and Erlangen at the factory was about 5 years older, and that could contribute to the differences. So what are the benefits of high performance gradients? Well, very simply, for echoplanar imaging, it makes all the difference in the world, because we can, instead of lengthening the gradient pulses in the read gradient readout to get higher spatial resolution, noting that it's the area under the gradient waveform that's proportional to the spatial resolution. Instead, we can make the gradient pulses a higher amplitude and steeper, and even shorten the TE and come out with an earlier TE and a shorter echo spacing. All contributes to improved image quality, higher signal to noise with a shorter TE, reduced distortions, susceptibility, blurring, and also reduced TR with the shorter echo train length, so we can get more slices or more 3D coverage. And here's an initial comparison holding the echo train time constant, so that's same point spread function due to T2 star decay along the phase encode axis of the API echo train. And the voxel size that we could achieve with more echoes and higher amplitude was 0.45 millimeter isotropic compared to 0.7, which is quite a big difference. It's a 3.7 times higher volumetric resolution that we could achieve on our scanner compared to the standard scanner with 80 millitesla 200 slew rate. This is the predecessor head gradient coil. Of course, if you go to faster echo readouts, the signal bandwidth becomes higher, and the signal to noise drops by the square root of the bandwidth. And so you have a trade-off. The TE is increasing the signal to noise, whereas the bandwidth is decreasing it. And the curve shows you there's an optimal point, but the point is that there is a trade-off. And so some multi-echo EPI studies, another example of application of the gradient coil, we could readily achieve 1.15 millimeter resolution compared to the previous 1.6 achieved on the predecessor head gradient coil, asymmetric gradient coil. And you see a difference in echo spacing. We can also achieve a fourth echo with somewhat relaxed resolution. Another comparison was to the same sequence run on a standard 7T scanner across the bay, San Francisco, at really a comparison at mesoscopic resolution of 0.6 millimeter, where really the gradients have an advantage, and is the resolution regime that we wanted to do research in. And you can see considerable improvement in image quality, overall signal to noise, artifacts, and using our receiver arrays, 64 channel, we have overall higher signal in the cortex area. And the echo spacing really was pushed out to 1.2 milliseconds at the scanner, conventional scanner, to achieve the resolution, and the TR was lengthened compared to our scanner 0.7. So everything fit as theoretically would predict. The receiver arrays, we actually had 3 different projects on developing receiver arrays, but it was really MRI Coil Tech, really Shahjahan Gudamoni, that came through and made our scanner work, because we could not fit conventional Nova Medical receiver array into our circular small diameter head gradient coil. So here's the 96 channel and 64 channel. You see really a high density of preamps and loops, and really a lot of things that can go wrong with wires not having exactly right, the soldering, or preamps burning out. This is all handmade. So it took a lot to troubleshoot. And when there were spike artifacts in the images, we had to really go to the bench and spend evenings and days looking for the problems, which we did. And we're now on to second generation designs of the 64 channel coil based on the original. But the signal to noise gains are quite noticeable compared to the 32 channel array, noting also that this is the Nova Medical coil. It has a slightly larger diameter for comfort, and the further the array is from the head, you do have a reduction of signal to noise. So there are two factors involved, but definitely the 64 and 96 even higher signal to noise and higher acceleration. This is the final configuration of the 64 channel coil. We use it really as a workhorse, not because we don't want to use the 96, it's just that it produces too much data, which is difficult to handle in the pipeline. And I think when we solve that, we will be using it much more. Notice the coil has rectangular loops, not circular loops. A couple of issues that we faced, and I think is unique to our scanner, to the gradient coil, which produces a very high E field, inside the magnet, is there was eddy currents produced from the return paths of the wiring in the back at the top of the head that heated up the shielding. And we shortened the shielding so that it didn't extend into this region and reduce the temperature. So that was one thing. The other was we spent time tracing down acoustic noise in our scanner. And there are two sources from the gradient coil, either vibrations or eddy current induced movement by Lorentz forces. And we found that to be true, the latter to be true, on the RF shielding. We changed the material to replacing the copper with this mesh shielding that had less an eddy current effect, and it lowered the acoustic noise by up to 10 dB and boosted the transmit efficiency. Here you can see on comparative curves with the new shielding versus the old. So this is a noticeable difference. Another project on the receiver arrays that we've been pursuing, again, very challenging because of the interactions with the gradient coil, high E field, that is affecting the transceiver switches. But overall, the general idea and project is to combine the outer transceiver loops with the inner higher densities array loops and receive from both of them at the same time. And you can do that by having a transceiver switches to switch on the transmit coil between receive and transmit. So the coil goes from a 64 channel receive array to a 72 channel, or with the 96 channel up to 112 receive loops. But the transmit loops cover the face area more completely than the receive array. It has openings for the eyes and the mouth. And that's one factor. And also just the difference in diameter and size of the loops plays in. And I want to mention that Minnesota group has also been developing this at 10.5 T. And I think, they don't have the challenges that we have because we have this SE72 gradient coil, much lower E field, and not causing the trouble that we're having. But nonetheless, we're getting successful results. And even this week, we finally seem to have it down, and it's working well. I'm sorry I don't have images to show you, but here's an example of signal to noise improvement in the middle of the brain. So we're clearly reaching now the ultimate intrinsic signal to noise in the center of the brain with about a 20% improvement there. So the goal is to really do whole brain imaging with layer fMRI. And I've really been directing the project toward that. And I think we've had, again, two different projects of whole sequence development. And Seung Park has been developing this variable density KP sampling with temporal random walk sequence, and it's produced very high quality images, and it's going well, but it isn't the sequence that we're using predominantly right now. We are using a sequence developed by Rudy Sternberg and Tony Stoker, the skipped KP3 to EPI sequence that Rudy and Renzo Huber have worked on and changed, optimized for vaso. And so here is some initial results we have in the visual cortex V1, and you can clearly see laminar activation in both V1 calcarine sulcus areas, and repeatability with a little bit higher 0.39 millimeter resolution, but repeatable day to day. We use the sequence again to go to whole brain vaso fMRI, and we can see the variation in activity across the cortex with laminar distribution. And these were really initial studies. The issue, though, is that with all of the different types of correction methods in the sequence, the TR and the larger number of inversion pulses, the TR for the total coverage of the two EPI and vaso data acquisition was on the order of 20 seconds. And that was just too long. And so Alex Beckett in my group has been working on the sequence, and we've been working with Renzo Huber, who has been working on removing image artifacts. I'll show this in a second. And the acquisition now is down to 4.88 second TR for the pair of images, and for whole brain coverage, it's slightly, giving up some spatial resolution to fit everything in with the echo spacing of 0.6. And it's really beginning to pay off. We get whole brain coverage and using it for movie watching and different paradigms. And we can use analysis used in functional connectivity studies now with our whole brain CBV weighted data that I don't think has been achieved before.
David,
Yeah.
just to say we're at 20 minutes. It's good to start coming to
How
the
many
end.
minutes? How many minutes?
We're at 20.
We're at 20. Okay, I'll move quickly. So some examples of standard analysis and functional connectivity in the matrix, present, identifiable in the vaso, and not so much in the bold at all. And other analyses like gradient analysis in the sensory motor associated regions on the top row, and other analyses that will be presented further this year. The artifact is that Renzo called fuzzy ripple had to do with the short-term eddy currents that are affecting the plateau of the read gradient. And by changing the polarity, every TR of the read gradient, so the first one is negative and then positive, you can combine the data and extract the artifact that was overlaying the images and get very good quality images. Just one last word on diffusion imaging. Obviously, faster diffusion pulses and EPI readout are going to shorten the TE and give you higher signal to noise. And we knew that, but we really couldn't understand why we were getting such good quality images. The 3D coverage has been very good. We can go to relatively high B-value and high spatial resolution, and working with different groups, Peter Basser's group. And we recently did a comparison to the Connectome 2 scanner, which they just published, and we could see that our scanner with 7T at 200 millitesla per meter has higher signal to noise by about a factor of 2 at these higher B values than the Connectome 2 scanner. So that pretty much explained why we're getting such high quality results, and a larger number of fiber crossings, up to 4. We're now looking at 4 or 5 fiber crossings that we really couldn't see before using lower B values. And doing some simple simulation, the explanation is quite clear. Our scanner with the cumulative gains of 7 Tesla higher magnetic field shown here combined with the shorter TE, but not as strong of a gradient. And the disadvantage is that the T2 is shorter at 7T than 3T, but it's overwhelmed by the gain of the higher signal magnitude. And so here we are on the next gen 7T, and here's the signal to noise, different B values, and the connectome 2.0. So, in general, the performance of the gradients and the receiver rays is really important. And I think it's pushing neuroscience imaging into a new regime. And other sites are getting the scanner with the impulse gradient installed with the Terra X software. Really no difference, just different application. And here's my group that contributed a lot to the work, as well as the collaborators I've mentioned and many I haven't mentioned. So thank you for your attention.
Thank you very much, David, for that wonderful presentation of clearly a very complicated talk. We've got about 6 minutes for questions. Feel free to ask questions, and Nikos, people can put them in the chat, is that right? Or raise their hand?
Yes, and I'll try to keep an eye on that. They can also raise their hand.
Oh,
I'll
it's
put them
not
in the
sharing.
chat.
Yeah.
But maybe I can get started with a question while people are thinking up theirs, if that's okay with you, Aaron and
Yes,
David.
go for it.
I was just wondering, these are amazing results, of course. I was just wondering for the rest of us that don't have a next-gen scanner. I mean, you showed us gains from a lot of different components. I was wondering what would be the easiest for us and the most efficient usage of funding, let's say, from our sides. Do you think the impulse gradient is the most important component, or the sort of investing in higher density receiver arrays, or what would be your view there for fMRI specifically?
Well, I think they've put similar gradient performance. GE has, Tom Fu has made a gradient coil for 3T, and I don't think it has the same gain. It's really the cumulative gains from all of the different subsystems put together. The receiver rays, higher cortical signal to noise, the 7T boosting up the signal noise. I think something that I feel I didn't expect. I thought the scanner would be really great for fMRI and, good for other things. But now I think that it's really the best scanner for diffusion imaging for neuroscience and the best scanner for fMRI. And I think for the field, it looks to me like going to 7T with these gradients, with at least 64 channel array, is really going to impact neuroscience compared to what you can do at 3T. Even if you put the strong gradients or a 64 channel array into a 3T. But if you only had, if you had to choose one or the other, I suppose the gradient coil at 7T, those cumulative gains are impactful most broadly. But then why not get the 64 channel?
Yeah, fair enough.
Thanks. So we got a couple of questions. Yeah.
I can read it
Yes, go for it, David.
Okay, so Jorg Jovic, excuse the pronunciation, a potential additional application could be dynamic full brain chemical shift imaging. This could be really interesting to better measure excitation inhibition changes. Whole brain chemical shift, yeah. We actually, with the Kubrick group, that came last month, and we did some experiments on diffusion spectroscopy. So having the 7T for the spectroscopy, and then the strong diffusion gradients, and the results looked very promising. But chemical shift, sure. Yeah. Thank you for that. So why do we choose square arrays for the receiver? And your AC84 was SR200, not the 400 we use. No, well, then as far as the gradient coil, AC84, it was a 400. The 84 stands for 8 for 80 millitesla and 4 for 400 millitesla. So that was just a typo. I'm sorry. And the square array for the receiver, you'd have to ask Shahjahan Gudamoni for that one. I think it's just for having great flexibility in design and shaping. And functional diffusion MRI compared with bold and vaso and cortex and beyond white matter. I'm not sure what to compare with bold and vaso. No, I think it's for more clinical applications of looking at different metabolites and separating them out with the spectra and diffusion. Xiaoping Wu, great talk, David. You showed the advantage of next-gen 7T over connectome 3T when comparing diffusion at 2 millimeter. So my question is, how high resolution could we go where we could still see the benefit of next-gen 7T? We're using B values of 35,000 right now, and we were processing the data. So we don't know. I think the answer to this question is we've really moved into an entirely new regime for diffusion imaging with high B value, supported by the high signal noise. And we need to optimize the different applications and different things. Joseph Vu, who's in my group and professor at UCSF, has been spearheading a lot of the data acquisition for this.
Great. Thank you very much, David. If we could hear applause, everyone would be clapping loudly right now. And I think with that, it's a good time to move on to our next talk, and I'll hand over to Nikos.
Yeah, so thanks, David, for the talk, indeed.
Thank you.
And now it's my pleasure to introduce Professor Steen Moeller from CMRR. I'll make it a little bit short. I think everybody knows that he has worked extensively on reconstruction, particularly for fMRI, and he has agreed kindly to give us his thoughts today on reconstruction considerations for improving data quality for fMRI. So, Steen, the floor is yours.
Excellent. Thank you so much, and thanks for the invitation to come and give this talk. I'm going to try to cover in this talk some of the highlights that I kind of that I feel I always get asked, like what should I do? What should I choose? And so my hope is there's going to be some takeaway considerations from this that people can actually go back and be like, this is what I do, this is what I get. So I was given the title of Reconstruction Considerations for Improving Data Quality for fMRI. Always advancing to the next slide. There we go. See how much delay there's in this. Okay, so obviously we can choose to acquire our data in different ways. Single slice, we did that 30 years ago. We went into kind of like the whole SMS world about 20 years ago. 3D acquisitions, we certainly did them many years ago. We're doing them again now. David also showed some of these, and we need to go to 3D just to do the really high resolution. Of course, when we acquire, we can do the single shot. We can do segmented acquisitions, which has a lot of benefits, but at the same time, there's so much work done on fixing segmented acquisitions, just because they normally don't. There are challenges with them. Again, 25 years ago, we went to undersampled acquisitions, and once we go to the undersampled acquisitions, we go into the reconstruction. And so here I'm just making a simple image of kind of like that we can do it in the image space, where we do the standard sense formulations, where we have sensitivity profiles. We just make one combined image by solving a simple, small linear system. The alternative, of course, is to do it in K-space, where again, where we replace the missing K-space data, again, solving a linear system where we have this A matrix, whatever, that does something. And so, sorry, for that. The A matrix is going to be a little bit of what I want to make sure that I get a little bit of across here. And I was asked to make sure that we don't talk too much about the small nuances of grapher. So I'm going to try to keep it at a high level a little bit. Of course, as we go and do our fMRI experiments, we constantly have to make these considerations, like how much noise do I want in my data? What resolution am I trying to target? And we will always have to balance those off. We want the highest resolutions with the lowest SNR, and we can't get it all at the same time. So when we get to the reconstruction on the sense side, there is something we can do explicitly. We can get our sensitivity profiles. My own preferred way is to do the e-spirit maps to that. And I think that most people probably do that. And then we can do this matrix regularization when we do the sense equation. It's a little bit hard to do, but people do it, and it's just because the system is very small, tend to be very small. It's like we have a few alias pixels, and we're just trying to separate it out. So it's a small, this E matrix for solving it out is small. So an explicit regularization is a little bit challenging, but people have certainly done it. In contrast, when we go to the K-space, we have our calibration data. That is the equivalent of the sensitivity profiles. And there's either an implicit, there's always an implicit regularization that goes into getting the A. Even though you don't dial anything in, there's an implicit regularization. And I think that is kind of like going to be my key thing from this talk, is that if you use one of these case-based methods, you're regularizing your reconstruction, and you got to just make sure that you know what you have traded off. And this is really the link that I wanna make people aware of, that for me bridges things a little bit together. So it's a paper that about a decade old, the paradoxical effect of the signal to noise ratio of graph calibration lines, a quantitative study. And of course, I just took AI and asked, well, what is this paper about? I'd read it beforehand, but the key that I wanted to pull out is that the noise in the ACS lines acts like Tikhonov regularization, stabilizing the reconstruction. And I think that is a concept that's important to be aware of when you're trying to think about, like, how do I want to do my reconstruction for my fMRI? And that is that the ACS data is kind of like they're applying a regularization whether you want to or not. So when I say that, what do I mean? So the noise is going to ask as a Tikhonov type regularizer. When we try to set up kind of like a simple linear equation here for finding this A matrix, these graphical matrices, we can add noise to our measurements, our case-based data, as we're trying to set up kind of like a source and target system. There's a place that one could argue that could be optimal. That means that each little part of K-space, you actually find an optimal A matrix that will reconstruct that. Normally, we don't do that. It would be somewhat computationally depending, but I'm not going to discourage anybody from doing that. But practically, we just add IID noise to all of our case-based data to kind of like lower the SNR. And so why does it matter? I'm giving you an example from 70, 0.5 millimeter, one-dimensional reduction factor of 4, and this is just for 3D PI, but it really is not too much. So obviously it's high res. On the left, you see kind of like just what a standard reconstruction can look like with a type of like a high SNR calibration data. You add some noise to your ACS data. That's all you do. Just add noise. Suddenly you actually get what some people might start to say is getting in a ballpark of a relevant image. And if you keep on adding more noise, the image is certainly going to have less noise on it, but you might start questioning a little bit. As with Grappa, we can calculate these G factors. So I'm actually just giving you here an example where adding a little bit of noise, make my calibration data a little bit noisier, can drop down the G factor, maybe by about a factor of 2. I'm showing them here just from whatever, 0.5 to about a factor of 6. So it might mean so these regions that have a factor of 6, that's where you've lost like 6-fold of your SNR. You've regularized it a little bit, and then you're down in half the ballpark, and I can keep on going higher, right? I mean, I can do, so this image on the right, technically, have 3 times the SNR of some of the other ones. One point I want to then caution about there is that we actually took these and scanned them for a long time series, averaged them up, so we got back into the high SNR regime, so we could appreciate the overall image quality. And now you can see that the image on the right certainly looks like a brain, but then there's misplaced signal, right? So the regularization gave a better SNR, but also misplaced signal. The one in the middle, that you might appreciate also, starts to have some small of these little artifacts showing up here and there. Whereas the one that we regularized the least, when we try to recover all of the SNR, actually just doesn't have some of those like little line artifacts that we can find here and there, which just comes implicitly from this regularization. So it's just one of those things that we do it no matter whether we want to or not. And so that is kind of like, to me, I'm thinking about this kind of like there's a biased versus unbiased effect here. In terms of that, if I want to have higher noise, I'm willing to accept higher noise, I can get a more unbiased signal. Whereas if I'm trying to drive down my noise, I'm going to kind of like increase this residual aliasing, point spread function, however we want to think about it. I want to go into talk a little bit more about these calibration data that we often use for the ACS. We often talk about that we can either do fleet, which is like a segmented EPI with just short TR. We can do a segmented EPI, has a long TR, more susceptible to some of these breathing relevant segmentation artifacts. Or we can do some sort of a GRE flash type sequence, which tends to be just a short TETR. And here I'm just showing kind of like a root sum square of what they look like. So clearly you can appreciate there's a big difference in the SNR level between these, also in terms of the artifact level between these type of acquisitions. And so we have to kind of make conscious trade-off, what do I like the best? And so that's what I want to talk a little bit about. About a decade ago, we looked into some of this a little bit. And so the point here is I wanted to compare kind of like this GRE that has no artifact compared to a flash. We did this as 7T, which is not the point here. We looked at it for like an IPAT factor of 2, so a phase encoding on sample factor 2, in the middle 3, and on 4. On the bottom is kind of like I just increased the off resonance to just show more like when we have more of a geometric mismatch between the calibration data, what are the effects really of that? Because that's one of the questions we often ask. Should I do high quality, but where the distortions don't quite match? So obviously, as I shortened the total readout time of the echo spacing, the effective echo spacing, the distortions get less. In all of this figure, the key thing is kind of like to look at the flash with an IPAT of 4 when the off resonance start going higher. You can start to see there's a little bit of shading in there. And that is kind of like just where some of the off resonance effect with a high reduction factor starts to pay in. Otherwise, if I look at these, there's not too much difference between a flash and a fleet, even though they're not distortion matched. So there's some shading when distortion matched for high, but it really just comes for high acceleration factors, in my opinion. We looked at a little bit about this and compared them at multiple runs. So we ran 6 series, and then we acquired all these plethora of different reference scans and applied them to the same series so we could actually compare them. So for reduction factor 2, we had 6 experiments, and here I just ordered them from the highest TSNR to the lowest TSNR. And you can see that whether I use like a fleet or a flash or a segmented reference, they have more or less the same TSNR. Go to a reduction factor of 4, there's a little bit more difference. My key point here that I wanted to take away is that the difference between the method is smaller than the difference between successive experiments. So often when we see some of these papers, some of these investigations into this, they do successive scans. I did this one, this method, and I need to leave them or whatever. But it's really hard to know this. So for me, there's a larger variation between scans than between methods. I want to point out that if I want to look at successive scans, the flash GRE, just because of its anatomical purity, to me, it seems like just more reproducible than some of these lower SNR in terms of kind of like getting the same image from successive scans. But of course, often when we do our fMRI analysis, we do various run-to-run corrections. And so that kind of like accounts for that. I want to go in and talk just a little bit about also the ACS sampling for SMS. Of course, this goes back to the whole idea of caipirinha. I just wanted to show kind of here, we do a caipirinha type experiment. We would do two experiments. So we have samples, say, in the facing code would be one experiment would be all the green dots here. The second experiment with opposite phase would be the red dots. When we do a caipirinha, we kind of like just jump between the two conditions all the time. Point being that if I go to like a multiband 5, I can think with a caipirinha shift that I'm kind of like just moving through K-space, kind of like shifting continually. So what we did initially was that we went into kind of looking at the slice grabber for doing the reconstruction. We calibrated on just this single pattern and applied it. Then we subsequent, and it was Karen Setzenpump did this. He did what's called the split slice grabber. Again, he calibrated on a single pattern and penalized it so that we to suppress down residual aliasing. The point that I want to make is that it's a very good implementation and efficient implementation of doing the concept of really making sure that you account for all different patterns in your calibration data. So again, the split slice grabber we prefer for a number of reasons, and we saw early on the reasons why getting the right calibration data is important. And so it's about reducing for the SMS. It's about trying to reduce false positives with the slice blocking recon. That's what we call it in this paper. And you can see that if we just did the slice grabber for this kind of like visual activation, you have residual aliasing in the brain. If you kind of apply the slice grabber, you don't have that same residual aliasing that is kind of like replicating throughout the brain. It comes at a cost. We looked some at the TSNR. And so on the top, you can kind of, we're showing here kind of what the TSNR is for the slice grabber. On the bottom, it is what the split slice grabber is. And so therefore, the SNR actually goes down, but the quality gets better. So similar to what I just showed with a one-dimensional grabber, is that we might sometimes want to make sure that we actually capture the accurate representation versus getting the better TSNR. So that kind of talked a little bit about the ACS data, a little bit of how do I train it, how do I want to make sure that I get enough calibration information that accurately represent all the different physics things that I want to capture. I want to talk a little bit here also about processing. And so one of the things that we often do is that we know is that EPI is very sensitive to our respiration fluctuations. So I'm here just showing some sort of a time series where we have multiple shots. Each of these dots represents an EPI readout. I'm just calculating a phase for the center from the 3-line navigator that fluctuates through time. So the dot ones is about a 4-second period. The green one is a 4-second period. And so that's why I just highlighted them up here. What we then normally do is that we can take each kind of like the phase that changed from shot to shot and kind of just correct our EPI train with it. The reason why I want to show that up is that we're measuring this with the navigator, but that does not actually end up translating necessarily to that is the phase that is really captured at the center of K-space. We're getting the top one that looks very nice in respiration like from the navigator. But when we actually go back to look at the center of K-space, it can actually have the phase in there can actually fluctuate very differently. And so sometimes you actually need to correct for that. And so this is one of the correction steps that we often do with our methods, and their current papers also online on bioRxiv that look at various different things, right? I want to also just talk a little bit about partial Fourier reconstruction. Of course, David did this a little bit more than a decade ago. He's going to say 90 something, but I'm not going to date David quite that much. But it's a long time ago that we started doing partial Fourier. When we just on the Siemens side, but that really doesn't matter too much. If you do a 6/8 partial Fourier, 7/8 partial Fourier, you often just do a zero padding. You can do what I'm showing on this big figure here is kind of like what the TSNR kind of like changes. So on the top row, you have 4 slices. That's kind of like just what we get from the vendor reconstruction. If we do kind of like some sort of a pox type reconstruction, the TSNR goes down. It does kind of like that. That is kind of like comes along with it. Being me, of course, we often do some thermal noise suppression. So we run that on our series. And so sometimes we can actually cover some of that TSNR back. And that can be preferential. My point here, though, is that I want to get to. This is kind of like an experiment that we've done with Luca Vicioli, is that when we get our data out of the scanner, even at this is a 5/8 partial Fourier on the vendor, they do their reconstruction. We get some sort of activation max. This is an auditory block, somewhat high resolution, 3D EPI doesn't matter. When we try to take account for some of these small phase changes, we do kind of like a better maybe pox type reconstruction, do some thermal noise suppression. We can actually get much better, more plausible looking activation maps. But this is very hard to currently dial in on the scanner, just because it's kind of like we're limited sometimes by the implementations of the vendors, whether it's GE or Siemens in terms of their POX implementations. I want to also just make a little pitch to this blog post by Renzo on layer fMRI. He has one where he talks about grapple regularization for the ones that are kind of like in the Siemens world. And I talked early on as to kind of like how we based on our ACS data, we have to get this linear matrix, and we can get at that one a couple of different ways. And so there's a way of actually getting into a full tuning all the parameters at the low level on the Siemens system. The hard part is actually knowing what you're tuning at, and Renzo went through some master thesis to actually unpack which parameters likely to tune at. And so there's a certain parameter that can be tuned in there, and I would suggest kind of like just reading the blog post instead, because that one actually will walk you through on some of the different platforms. Again, it kind of like does explicitly what I tried to do implicitly with kind of like just tuning the SNR of the calibration data. So here in my summary, I kind of like just want to say, of course, the quality of the calibration data matters. It can't be any other way. Ghosting in the calibration means ghosting in the recon. So when you want to tune your fMRI experiment, if you're ghosting, it ghosts. Low SNR in the calibration, it regularizes it, and you get some of this possible residual aliasing. High SNR in the calibration is another devil, right? There might be a very excessive noise amplification, and either you add noise to it or you go in and you try to tune some of these regularization parameters in the graphic calibration or the ARC calibration. To me, ACS that match with the imaging SNR seems to be the most appropriate. That's kind of like the one that intuitive to me makes the most sense. As I showed, the variation between some of these different methods for getting ACS calibration tends to be bigger between different runs versus the methods. To me, segmented EPI is probably the most favorable for the speed, assuming that you have a low segmentation ghost, which is a high assumption to have. Fleet has less ghosting and more regularization. That is kind of like just when you see the difference between the two, you got to. I'm encouraged to appreciate that's where the differences are. What the data is calibrated on matters. Kind of like if I for the SMS, I kind of like show, do I calibrate it on all different multi-bind pairings, shifting, and K-space, and similar things for more complex physics changes. We need to make sure that we calibrate on it so that we actually do the linear systems, because in general that should just work fine. For reconstruction, specifically here I showed the partial Fourier. The vendor implementation likely favors stability for imaging versus optimality for fMRI. And so in terms of going in and looking at things, how do I do it best? There's a space in there that people can look at. Thermal noise post-processing, whether Nordic or any other of these other methods, may interact with some of these choices. And so those are kind of like things that I felt would be helpful to cover in what I perceived here. And I hope that everybody kind of got an idea of some takeaway methods in terms of like what it means for the experiments. And of course, lastly, acknowledge the people I've worked with for quite a long time, and also our grant funding. Thank you.
Thank you, Steen, for this talk. Super interesting. I would like to let people know that we have now figured out how to allow you to unmute as well. So if you raise your hand, I can I give you the space to do so. Or again, you can post your questions in the chat or in the Q&A as well, and I will read them out loud. Any questions from the audience? Please raise your hand. There we go. Let's try it with Xiaoping. I think you should be allowed to talk now.
Yeah, thank you. Can you hear me?
Yep.
Okay, great. Thank you, Steen. Very nice talk. So I have a question about the calibration. So you mentioned the impact of noise in ACS on GRAPPA. So the question I have for you is, could you comment on the noise, the potential impact of noise in, let's say, calibration when it comes to sense reconstruction? So in other words, should the noise in calibration also match with the data when it comes to sense recon, or it should be like the higher the SNR, the better when it comes to sense reconstruction? Thanks.
So, for sense, the impact of the noise would be on getting sensitivity profiles, and so to me, that's kind of like where I normally run an eSPIR type reconstruction, which is of course a very low pass filtered version of getting sensitivity profiles. So I think you need to have some amount of SNR. But I would actually favor doing an eSPIR on the GRE flash type data, just because in that case you don't have any aliasing artifacts. I would probably, if I go the sense way, I would be hesitant probably on using the segmented EPI, because I think you're going to be more susceptible to just small amount of ghosting in the data.
Okay, so you think most it's not necessarily the SNR is a potential artifact in the calibration data when it comes to sense.
So for sense, I don't think the SNR is a particular artifact, because I think you'll more easily be in terms of SNR in a regime that works reasonable.
Okay, cool. Thanks.
We have a question from Joseph Pu in the Q&A, so I'm going to read that out loud. Using the CMRR C2P or maybe the Siemens product sequences, can you recommend methods to adjust the ACS CNR? Should we adjust the number of ACS lines or the flip angle or something else?
So I would adjust the flip angle. I would hands down adjust the flip angle. It's kind of just make sure that we kind of like drop it down low enough. I think that if we go with too few ACS lines, and I think especially for fMRI, where we get an initial reference calibration scan, it's easy to get enough ACS lines. I think you want to get enough ACS lines that you kind of capture the right physics, and then you just want to get low enough SNR that you kind of regularize your way through it. And I think if you go with few ACS lines, in certain ways, your linear system hasn't seen all the full dynamics of it.
Thanks. I think in the interest of time, I may try to move on. Let's thank Steen one more time for this beautiful presentation. And I'm gonna move on to our last speaker for today, who is Caroline Le Ster. She's working at CEA at NeuroSpin, and she has worked extensively with 11.7, but also with low field strength magnets like 70. And she also has a lot of experience across the whole fMRI spectrum, and also magnet interactions with gradients and all sorts of artifacts that may arise. So yeah, the floor is yours.
Can you see my presentation?
Yeah.
Okay, great. So thank you for the introduction and for the invitation. I'll start with a quick reminder of the interest of ultra-high field for fMRI. So the SNR increases with the B0 field as a complex function of the object size, shape, and composition, And Ralph Bowman had a nice experiment where he measured the SNR in the brain at different fields using state-of-the-art sequences and realistic state-of-the-art coiled and realistic sequences. Sorry, and he was able to find a relation that the SNR increases with B0 to the power 1.65 in the cerebrum. This means that when we increase the SNR from the field from 3 Tesla to 7 Tesla, we can expect an SNR gain of 4. So this SNR gain, it can be invested either in spatial or in temporal resolution. If we choose to increase the spatial resolution, it means that for the same acquisition time, we can acquire images at 1.6 millimeter isotropic at 7 Tesla compared to 2.5 at 3 Tesla. It means also that for our EPI sequence, we'll have to acquire more echoes, and that will be more sensitive to the subject motion. When we increase the magnetic field, we have also a change of the relaxation times, and the T2 star shorten both in the white matter and in the gray matter. So for our EPI sequence, still we have to shorten the echo time, which comes in contraindication with the more echoes to acquire. So in the end, we need strong gradients to perform fMRI at ultra high field, and for instance, the impulse gradient coil that David talked about. There are many challenges when performing EPI scans at ultra high field for fMRI studies. The first one is the increased B0 field inhomogeneity. So the B0 inhomogeneity comes from the main B0 field inhomogeneity of the scanner, but also when we place the head of the subject in the scanner, it will create a non-uniform delta B0 distribution that originates from the susceptibility difference between the air and organic tissues. A way to restore a homogeneous B0 field in the brain is to perform shimming. There is a passive shimming that is performed when the scanner is installed on site that consists in placing some ferromagnetic pieces on the magnet bore. There is also active shimming where we have some dedicated coils into the scanner that can generate spherical harmonics, shaped magnetic fields that are specific to the patient. And the scanner manufacturer includes shim coils to the second or to the third order. And also some sites have developed their own additional local shim array to go further than the third order. For instance, in NeuroSpin, we have the device developed by Bruno Meneses. Even with these field homogenization steps, we still have some strong field excursion in the brain that persist after shimming, and these excursions are stronger when the field increases. As a consequence, on our EPI images, we will have some geometric distortion in the phase encoding direction and the signal loss due to intravoxel dephasing that results in a shorter T2 star. Another challenge of EPI scans at ultra high field is that we have to cope with an increased B1 plus inhomogeneity. So the B1 plus profile, it depends on the RF coil type and the sample. And as you see on this figure, when the field increases, there will be some shadowing and hyper signal areas that are caused by dielectric resonances and field focusing effect. A way to cope with this is to use dielectric pads at 7 Tesla or parallel transmission. So parallel transmission consists in using an RF coil with multiple transmit elements that are capable of transmitting different RF pulses on each port. I'll be quick on this part, but we can use either static RF shimming or dynamic PTX, and that's what we use in NeuroSpin, the PTX, with universal pulses. It means that when we scan a new subject, we don't have to design a specific pulse for this person, but we use one that was designed offline on a database of delta B0 and B1 plus maps. Here it is an example of how we can restore a homogeneous B1 plus excitation in the brain with universal pulses. And so for our EPI protocol, we usually scan at the Ernst angle in order to maximize the SNR. So we are quite robust to the B1 plus inhomogeneities, except in the cerebellum. But since we want to achieve the Ernst angle in the cortex, we usually overshoot in the center of the brain, which means that we can reach the SAR limits quite easily, especially with the SMS EPI sequence. Now I'll make a reminder on the hardware and the system imperfections. So here it's a schematic view of a scanner with the magnet and the helium bath. into which fits the gradient coil that is connected to the shim cabinet and the GPA that are located in the technical room, and the connection is ensured through the filter plate. The gradient itself is composed of different layers that we are going to see now. The first one is the primary coils. There is a schematic view represented on this figure. So the role of these primary coils is to generate the time-varying magnetic field gradients along X, Y, and Z. There's also water cooling in order to remove the heat that is generated by the ohmic losses. The high-order shim that we just talked about, the passive shim, it's usually iron plates that are inserted during the installation of the scanner. All of this is embedded in an epoxy matrix, which aim is to achieve optimal stiffness and stability of the gradient coil. And there's also a shielding coil on the most outer part of the gradient in order to minimize the gradient field outside of the coil and minimize the eddy currents. Our ideal gradient system would have a high amplitude, a high slew rate to rapidly switch in the fast sequences. It should also be linear to reduce the distortion and accurate, of course. It's not only the gradient that is important, but also the gradient power amplifier. So it's a cabinet that is located in the technical room and it drives the gradient coil. And the performances of the gradient and the GPA are closely related. So as we can see, all this is very complex technique. So it comes, of course, with some imperfections. The most famous one is the eddy currents. So there are some unwanted electric currents induced in the conducting structures of the scanner when the gradients are switched rapidly. And there are always multiple eddy currents that coexist with different time constants. The eddy currents can be quite well predicted. Another imperfection is the heating of the gradient system. So the water cooling does not fully compensate for the heat generation, and the gradient can heat of tens of degrees in a few minutes. If we look here, for instance, we have some temperatures provided by the Siemens per coil temp file. So it's 12 sensors that are located in the gradient coil and provide temperature during the scan. And we see that for the sensor one, there is an increase of 30 degrees in approximately 9 minutes. So why this is important? It is because the gradient response is modified with heat, and it is very challenging to predict. So that's why it's always advised to make a first EPI scan without the paradigm before acquiring the real fMRI protocol. Other imperfections include mechanical vibrations. So when we run a current into the gradient coil, it will induce a Lorentz force that causes a displacement of the gradient coil. For instance, here on our 11.7 Tesla scanner, we taped some accelerometer in order to characterize these displacements. And we measured some quite strong acceleration and displacement of the gradient coil that increase with the B0 field. There are also some mechanical resonances of the gradient that we will talk about later. And also when the scanner hits during the fMRI scans, for instance, there will be some higher order B0 drift because of thermal changes in magnetized part of the system, for instance, due to the iron shim that is here for the passive shimming. So all of this has some consequences on the B0 field. It will cause some imperfection that can be either linear or of a higher order, constant or varying over time, and last for a short or long term. So it's very diverse consequences. And on our EPI images, it will result in distortions for the Cartesian acquisition, blurring for the non-Cartesian acquisition, ghosting, shift, etc. And it is detrimental for fMRI because EPI are especially gradient-demanding sequences that use long readouts, and also because these artifacts will affect the temporal stability. There are some solutions that are already implemented on the scanner. We discussed already about the shim that reduces the B0 excursion, the gradient shielding that prevents the eddy currents. There is also a pre-compensation of the gradient waveform. You can see on the blue figure when we want to play a nominal gradient, there will be eddy currents that will add up and will distort the gradient that is actually played by our system. So if we know that, we can precompensate our gradient to obtain the nominal shape. There is also a eddy current compensation during the reception and the post-correction of the acquired data, for instance, to correct for the non-linearities. So in the end, the gradients are much more reliable today than they were in the past, but there are still some imperfections that remain, and it is especially problematic for the advanced MRI methods. And many of these artifacts could be corrected for if we know the actual magnetic field and gradients. And there are many methods that exist for measuring and correcting the field imperfection. It can be some calibration in the sequence or some specific sequences, or the most efficient way is to use field monitoring. So the last part of this talk, I'll talk about the system characterization and how it translates to fMRI studies. So a very efficient way to characterize our system is to compute the gradient impulse response function. It's also called the gradient transfer function in the frequency domain. And the figures I'm going to show are from the original paper. So ideally, in order to obtain the transfer function, we would like to play a Dirac, but it's not possible, of course. So we will play 12 triangular blips on each axis, S, X, Y, and Z, with increased duration. And this allows to cover accurately a wide range of frequencies. So that's our input. We see here all the frequency covered by these blips. And we are going to measure the temporal field response using the field camera. So we have the actual gradients recorded at various spatial orders that are estimated output. And we can then very easily compute the transfer function with the formula provided here. So what we see first is that the gradient has a low pass characteristics. And if we look at the low frequency close to 0, I'll try to make a pointer. Okay. So if we look at frequency close to 0, that's where it's very important to look at the presence of peaks, either in the magnitude or in the phase. Because this deviation from the unit response, they will have some strong consequences on imaging. So once we had our 11.7 Tesla magnet running, we decided to perform the GTF measurement in order to see the response of our gradient to the field. And we saw a strong excursion at a frequency of 1350 Hertz, as represented here, of about 5%, which is quite important. So we asked some other sites that were equipped with the Terra system to perform the same measurement. And we saw also that they have this comportment, this excursion at 1350 Hertz. So we decided to spend a lot of time to try to investigate this further and try to understand where it is originating from, because it has some strong consequences on the images. And so we performed some mechanical simulation that you can see here of this SC72 gradient coil that equips our ISOLT scanner as well as the Terra. And we see that when we excite the gradient coil at 1350 Hertz, it will make a deformation of the gradient that looks like that. So it's a deformation that is perpendicular to the z-axis. It's called the breathing mode of the gradient. And it is caused by a mechanical vibration of the gradient that is induced by a Lorentz force. And it leads to this resonance at 1350 Hertz. And we think that is caused by a mutual inductance with a current that is flowing from the gradient coil to the shim cabinet through the filter plate. So a way to handle this is to unplug the third order shim coil at the filter plate. And you can see the result here on the GTF measurement. When we unplug the third order shim coil, we can reduce drastically the amplitude of the peak at 1350 Hertz. And very recently, we received the new 7 Tesla scanner in NeuroSpin, and we were able to measure the GTF of our Terra X. And the good news, it seems that the peak is slightly reduced on the terax compared to the tera at this specific frequency. Also, it's very important not only to look at the self-terms, so for instance, how Z acts, but also how the Z-axis, the Z gradient acts on the B0 field, and we'll see that in a few slides. We can illustrate this problem by having a look at an EPI sequence that will be kind of the worst case. So it's an EPI sequence that has its gradient along the Z-axis, readout along the Z-axis, with a specific echo of 1.11 milliseconds. And this specific echo will strongly excite the 1350 Hz resonance, because if we make the Fourier transform of this EPI train, the third harmonic corresponds to 1350 Hz. So if we look at the EPI plateau, as represented here in a zoom, we see that they are absolutely not flat compared to the nominal input in red. They are a bit distorted by these vibrations. And also, this plateau do not have the same shape, whether we are in the beginning or in the end of the EPI train. And also, there are some field fluctuations that occur after the end of the EPI train and that last for tens of milliseconds. So that was just a theoretical example. It's not really a realistic protocol, the previous slide, but then we decided to have a look at what happens in a more close to the field EPI. So we wanted to target a resolution of 1.2 millimeter with an axial 3D EPI sequence. And we increased in purpose the TR in order to have a better look at our sequence. So we see here a classical 3D EPI sequence with our RF pulse and slice excitation, the EPI train, rewinder, and imaging spoiler, and at the end, the fat spoiler. Now we look at the B0 excursion that occurred during this specific sequence. And we see some oscillation of the B0 field that occur both during the RF pulse, but also after the rewinder and imaging spoilers. They have a frequency of 1350 Hz. Also, there is a beating phenomenon where the oscillation disappear and reappear a few milliseconds later. And this B0 oscillation lasts for a very long time, approximately 35 milliseconds. So these one here are caused by the rewinder and imaging spoilers, but the fat spoiler also causes some additional B0 oscillation that will occur, that will happen during the next RF, because it is very close in the sequence diagram. And this is very problematic because it can affect the RF pulse, these oscillations, especially when we use some PTX pulses, so parallel transmission pulses, because then we need to have a phase coherence among the sub-pulses, and it can be destroyed with these B0 oscillations. A way to cope with this is to, and that's what we chose to do on our Isolt magnet, is that we combine the spoiler and rewinder with the fat spoiler. So we move this spoiler here, and we change the shape of the gradients in order to have them a bit more smooth and avoid exciting the 1350 Hz resonance. Another option is to choose widely the TR. For instance, we can choose to have a TR that comes just after the oscillations. So it's degradation of the volumic TR, but it comes at better image quality. So I realized I forgot to put images. So I just added a nice image that we can obtain on Isolt. So it's an example of fMRI image for a protocol that was at 0.8 millimeter isotropic resolution with a volumic TR of 2.7 seconds. So we use the 3D EPI sequence that embeds servo navigation with the prospective motion correction and B0 correction. And we can see that the image quality is very decent. So it's just to illustrate that when we take good care of all these issues, we can have a very nice fMRI EPI images. And here we use this specific sequence to study the numerosity in the superior colliculus.
Caroline, you're at 20 minutes.
Okay, I'll do quick.
Sorry.
So another interesting result from scanner characterization is to identify the fuzzy ripple, the identification of the fuzzy ripple artifact by Renzo Huber. So this is a strong limitation of high-resolution fMRI protocols, and it is defined as a local ghost with a low spatial frequency envelope of phase interference patterns. So you can see here it's a dark band that occur in the images, and it is caused by gradient imperfection. So it's a short-term eddy current during the ramp sampling, and it occurs especially when using high Grappa acceleration factors. And here again, it can be mitigated when unplugging the third-order shim coil, as you can see on this animation. And it was nicely demonstrated by Renzo that when he unplugged the third-order shim coil, he was able to retrieve some activations in a protocol where the activation were in the area affected by fuzzy ripples. So a strategy to get rid of these fuzzy ripples is either not to use ramp sampling. It's of course something we don't want. We want to avoid. So we can unplug the third-order shim coil, or another strategy that we can combine with unplugging the third-order shim coil is to acquire images with dual polarity readouts followed by a complex value averaging, and it is very powerful to correct these artifacts and also to increase dramatically the acceleration factor. The last slide. I just wanted to illustrate further the interest of characterizing the scanner for fMRI studies. So for instance, with the impulse gradient coil, we measured the gradient transfer function and we showed that there is no strong peaks. So because we want to have the impulse gradient on our ESOLT system, and we shouldn't be too much worried to have artifacts on our API images because of this smooth profile. And also it's possible to reconstruct the images with actual trajectories and B0 field by monitoring the field with a field camera, or by predicting the deviation from nominal trajectories with the GURF. So this is especially problematic for the non-Cartesian sampling schemes. And the correction is made by integrating the actual phase coefficient in the signal model. And then we have some non-Cartesian data. So to reconstruct the images, we have to make a regrading and a non-uniform Fourier transform. This was applied here in NeuroSpin for the 3D sparkling fMRI experiment, which is a very exotic trajectory. And we can retrieve a nice image from a quite blurry image. But this complexifies a lot the experiment. And with this, I'm done. Thank you for your attention.
Thank you, Caroline, for this beautiful presentation. Do we have any questions from the audience, or for that matter from the panelists? You can just raise your hands and I will unmute you.
Well, I can ask a question while we wait.
Yeah. Sure, yeah.
Really good talk, Caroline, and it's really thorough, all the investigations that you and your colleagues have done. I am wondering if you've noticed or investigated, and forgive me if maybe there's no physical mechanism for this to happen, RF-induced eddy currents. So I don't know if it could be related to RF heating, but I've noticed fluctuations after RF pulses without gradients, if that's something you've come upon.
Yeah, no, we didn't investigate that, but we did notice some instability of the RF over the fMRI experiment, indeed, which is, of course, very problematic. But it's quite hard to investigate, unfortunately.
It is, and they're much more localized than the gradient ones, so it's hard to pinpoint them. Thanks.
Any more questions? You can just raise your hand and I will unmute you, or you can put in the Q&A. In the meantime, maybe I will ask. Oh, sorry.
we've got a question
we
from
do.
Xiaoping.
Excellent. Okay, Xiaoping, I think you should be able to talk now.
Okay, thank you. Very nice talk, Caroline. So,
Thank you.
I have a question about how you modulate the spoiler along with the FASA gradient to reduce the impact of that magic frequency around
Yeah,
14K. So the question being, so what if I don't have the FASAT? So can we still do this trick?
Yeah. It's actually the sequence from Rüdiger Steenberg. So that's him who implemented this option in the sequence that we can modulate the ramp of the gradient and the duration of the plateau, but also we can have a specific ratio of ramp and plateau in order to specifically avoid the 1350 hertz. And if you don't have the FASAT, I don't think it's an issue.
Okay, in other words, it doesn't have to be like two gradients.
No.
If you only have one
They
gradient,
are
you can
fully
also do the
combined.
trick to. Okay, great, thanks.
Yeah, and actually we don't use a FASAT in the at 11.7 Tesla because it's quite it's not necessary because fat is too far away from water.
Okay, thanks.
It's a nice surprise.
I guess there's some benefit in
Yeah,
these
sure.
high
In the
fields,
SAR.
right? I also had a question in the spirit of the sort of theme of the meeting, which was a sort of practical advice. Besides unplugging the third order SIMs, what else would you advise the audience to do to maybe check whether they can improve their fMRI quality?
Yeah, so for us, we want to avoid the sagittal acquisition because of this z-axis problem. So we have some actual slices, which is a strong limitation, of course. Otherwise, because it's the 3D PI sequence, so it's very specific compared to what is done at 3 or 7 Tesla, where the SMSC PI sequence is more common. And our sequence has this prospective motion correction, etc. So it's very specific. But yeah, I would say that when we have this high resolution and strong physiological noise, having prospective motion correction is a strong bonus.
Thank you. Any more questions? Last thoughts? Otherwise, we're just on time, I think, to wrap it up. All right. I would like to thank all the speakers for joining us and the moderators and, of course, all the attendees. And I will try to share the recording as soon as possible. Yeah, thank you for joining us again.
Thank you.
Thank you, everyone.
Bye-bye.